Hello everyone, and I'm back again with another video. So hi, my name is Antoinette C. Pahanoy of PSECE 3A, and for today, for my subject ECE 23, I'm going to discuss to you a certain topic in my performance task number 4, and that will be about differential postcode modulation. So for the objective, of course, defining to you what is a DPCM means, and the importance of DPCM when transmitting and receiving digital information, as well as the applications, advantages, and giving an example for DPCM or differential postcode modulation. So quick overview, what will be the postcode modulation? That is where the DPCM is under. So it is a technique by which analog signal gets converted into digital form in order to have a signal transmission through a digital network. So that is postcode modulation, and to the right side here is a figure that shows the illustration of redundant information in PCM. And this second illustration giving you a hint, or at least where is the DPCM can be found. So also DPCM is the difference of in a sample of levels. So for example, that will be the first level, that will be the second level, assuming that this is the difference or differential postcode modulation in this PCM illustration. Also, what is differential postcode modulation? So it is a code words represent differences between samples, unlike PCM, where code words representative sample value, and where it's also a procedure of converting an analog into digital signal in which an analog signal is sampled, and then the difference between the actual sample value and its predicted value is quantized and then encoded, forming a digital value. So this is the block diagram of a DPCM transmitter and DPCM receiver, or also called an encoder and decoder. Design of DPCM system means optimizing the predictor and quantizer components, because the quantizer is included in prediction loop. There is complex dependency between the prediction error and quantization error, so joint optimization should be performed to assure optimal results. But modeling such optimization is very complex, so optimization of those two components are usually optimized separately. And of course, I'm going to discuss it later separately as well with a given example. It has been shown that under the mean squared error optimization criterion, apart constructions of the quantizer and predictor are good approximations of joint optimization. Coding a difference is based on the fact that most source signals showed significant correlation between successive samples, so encoding uses redundancy in sample values, which implies lower bit rate. And here is the block diagram of DPCM transmitter or the DPCM encoder. So let's start with the sampled value. That will be the example or the given example that we are going to use to solve these equations or the values of these certain equations here. So this will be XQ and TS is the prediction filter input. How do we get that? We just need to get the sum of the ENTS and XQ and TS, which is like identified as the input quantizer. This will be the output quantizer, the EQ and TS. And finally, we can get the digital data later, which will be represented by this equation. Now we have here an example. So for my example, I'm going to use this number 2.1, 2.2, and so on and so forth. This will be the example or the sample given. And also, how do we get the x raised to n and en and eqn, and also the xqn. So as what I have mentioned, the xqn, this is the prediction filter input. So this is the en is the input quantizer. So how do we get that? We need to get the difference using the sample given here, and we are going to get the difference from the xn, which is the result of this output quantizer that we have. And how do we get this EQN? This is the result or the round of number, round of value of this here, of the input quantizer. So for example, we get 2.1. So initially, in prediction filter, assuming we are going to first initially for the prediction filter, that will be 0. So 0 as follows. So we are going to put 2.1 minus 0 or 2.1. EQN will be 2 because round off of 2.1, the 2. And then we're going to get the value of the prediction filter input. So we just need to get or to add this 1, 0, EQN is 2 and 2. And then how do we get the next values here? We're going to put this value into here, and then this one into here, and so on and so forth, and then just copy. And then for the final, we do have the DPCM digital sequence. We're going to use this kind of input later for the next block diagram, which is for the DPCM receiver. So as what we have here, this will be the 200100. We use this value. And if we're going to use the transmitted sequence in 3 bits, that will be 010, 00, as what we have learned or before that on how to identify bits for these values. 010, so on and so forth. That's how we get that one. So yeah, for DPCM receiver, as what I've mentioned, this value that I've given here, we're going to use this one as the B for the input for the DPCM receiver later. And we are going to get the EQNTS, XQNTS, which is the prediction filter input, and this is the input as well for the decoder. And this is what it looks like here. So finally, we'll get the low pass filter CW signal and or the received signal later. So this is a table showing to you how we can get the value for the received signal. This is the result already, and this is the given example that we have already at first. So for the EQN, as what I've mentioned, we've used the digital data sequence that we have on the first, the result of the first table or calculation that we have. So 200 and 100 and follow. So how do we get this one? We're going to, of course, make sure initially it starts with 0. And then we're just going to add this for us to get the predictor, filter input or prediction filter input. So that will be 2 plus 0 and then 2. And then follow here, we're going to put the value in here and then add this as well on the given input here. That will be 2 and then put it here and then add again and 2 and so on and so forth and then copy. For the applications, let me go back. Anyway, this is the result, is what I've told you. So this will be the received signal, the 2.2, 2.0, and 3.3, and then 2.1, 2.2, 2.3, and the transmitted signal. The applications of DPCM. This technique mainly used for speech, image, and audio signal compression. In images, there is a correlation neighboring pixels in video signals. The correlation is between the same pixels in consecutive frames inside frames. This method is suitable for real-time applications. And for the advantages of DPCM, it's the bandwidth requirement of DPCM is less compared to PPCM. And quantization error is reduced because of the prediction filter. Number of bits used to represent one sample value are also reduced compared to PCM. And for this summary, as what I have discussed to you, what's DPCM or differential postcode modulation, which is just my topic, and how the transmitter and receiver done through a specific calculation using a block diagram equations. And for the DPCM, is just so you know, it is also called as an error signal. It has less levels, less number of bits per level samples. And for the PCM, it's the original signal. It's more levels, more number of bits per level samples. I guess that's it for today. And I really thank you for watching and listening as well. And see you on my next video. Goodbye.